Hi everybody, it's Mrs. Seitz. Today you're going to be working on lesson 5.2, which is bisectors of a triangle. Up until this point, you've been talking about perpendicular bisectors and angle bisectors, but today we're going to be putting those properties into a triangle. So your objective today is to use properties of perpendicular and angle bisectors of a triangle. So the first thing I want us to fill out on our notes today is a perpendicular bisector of a triangle is a line or a ray or a segment that is perpendicular to a side of the triangle at the midpoint of a side. So when we take a look at this triangle that I have right here, you can see that this would definitely be a perpendicular bisector because it's cutting this side into two equal pieces, because you can see the two tick marks, and we can see that it's coming down at a 90-degree mark. So we have a perpendicular bisector of that side of the triangle. So when you have three or more perpendicular bisectors that intersect at the same point, we have a special name for that. And those are called concurrent lines or rays or segments, okay? If you have three or more of these lines that would intersect in the same point, and we're going to see that on the next slide. So whenever you have those concurrent lines meeting up in a point, we have a special name for that too, and that special point is called a point of concurrency. Okay, so when we talk about the three lines that are coming together, those are called the concurrent lines. But when we actually have them meet up in a point, those are called a point of concurrency. So when we take a look at the pictures that you see now here, the three perpendicular bisectors of a triangle are concurrent, and the point of concurrency can be inside the triangle, on the triangle, or outside of the triangle, and that's important. But one thing I want you to notice is whenever you have an acute triangle, it's always going to be inside of the triangle. When you have a right triangle, it's going to be on the triangle. And whenever you have an obtuse triangle, it's going to be outside. So we're going to write that down. And the special point of concurrency when you have three perpendicular bisectors on every single side of the triangle is called a circumcenter. And the picture that you have right there of the three triangles, that is an example of a circumcenter of a triangle. Okay, so if I asked you, where's the circumcenter going to be of an acute triangle, you would say it is inside of the triangle. If I asked you where the circumcenter of a right triangle is, it's going to be on the triangle, and the circumcenter of the outside would be on the circumcenter of a triangle. If an obtuse triangle would be outside. And again, a circumcenter is made up of perpendicular bisectors on every single side of the triangle. So we actually have a theorem that goes with that. The perpendicular bisector of a triangle intersect at a point that is equidistant from the vertices of the triangle. So when I take a look at this, I can tell that this triangle has been made up by perpendicular bisectors. And here's how I can tell. When I take a look at the concurrent lines, I can see that there are tick marks here on the side of AB, so that I know that that's been cut in half, and I can see that it's been cut by a perpendicular bisector, so I see that right angle mark. I can also see here on the side length of AC that that's been cut in half by a perpendicular bisector, and from the side length of BC, I see three tick marks. and I can see that that's been cut by a perpendicular bisector as well. Okay, so if I have the point of concurrency that's made up by the perpendicular bisectors, this theorem says that if I have perpendicular bisectors and they intersect at a point, so that point is point P, then I can say that that point is equidistant from the vertices of the triangle. So point P is equidistant to point A as it is to point B. So PA is equal to PB, which is also equal to PC. Okay, so all of these guys are equal to one another if you have perpendicular bisectors on every single side. And again, the key word is equidistant. Okay, here's an application of this. So let's say, for example, we have 3 boats that are positioned out in the water, okay? And we have that the boats are equidistant from a buoy. So again, equidistant is the key word. Where is the buoy? Well, I actually made a construction, okay? And if you guys have your compasses and you have a ruler nearby, I would suggest that you create perpendicular bisectors out of each side length out of between the boats, okay? And if you don't have one of those, if you kind of just want to sketch it for note purposes, that's fine. But what I created was a perpendicular bisector out of each side length, okay? And then what I did is I extended each one of the side lengths, okay? One thing I want you to notice is when I connected the points between each one of the boats, you're going to see what kind of triangle you have. This is an obtuse triangle. And whenever we have this type of construction that's made up of perpendicular bisectors, remember this is called a circumcenter, okay? And when you have a circumcenter of an obtuse triangle, the location is going to be created outside of the triangle, that point of concurrency. Okay, now, since I know that this is equidistant from the buoy, okay, then the location has to be outside because I have this obtuse triangle that's created, okay? So to answer the question, where is the buoy? We're going to say outside of the obtuse triangle. Okay, and again, the key was equidistant, okay? Because I knew that this was equidistant, I knew that I was talking about perpendicular bisectors. So because of that fact, I knew that the distance from the buoy to every single one of the vertices had to be the same length, so I knew that it had to be made up of perpendicular bisectors. So when I created my perpendicular bisectors, I saw that that circumcenter was created on the outside. So again, up to you if you want to create it. I think it would be good practice for you, but for note purposes, if you just want to sketch it out, the perpendicular bisector was created on every single one of the side lengths from every single one of the boats, and it was created outside of the obtuse triangle. All right, so let's try this next one together, okay? It says the perpendicular bisectors of triangle PQR meet up at point S. We want to find PS and QS. Okay, so let's see where PS and QS are first of all. Okay, so here's PS and here is QS. And we know this whole thing is made up of perpendicular bisectors, okay? And another thing that's going to be very helpful to us is we actually know the length of SR. We know the length that SR is. It is what? 10, okay? Okay, now the other thing that we know is that this is actually made up of circumcenters, right? Because if you take a look at every single one, this is made up of perpendicular bisectors. And the reason why I know that is because every single one of the sides of the triangle have been cut in half, and they've been cut in half by a perpendicular line. So this has been made up of a perpendicular bisector, and it tells us that in the problem. So we just learned a theorem that says, and I'm going to go back to it, that if you have perpendicular bisectors, then there's an intersection point that is equidistant from the vertices of the triangle. So let's go back to that. So that means that PS would have to equal QS, which would have to equal SR. And guess what? We know what SR is. SR is equal to 10. So that would have to mean that PS would have to equal 10, and then QS would have to equal 10. Okay, and again, that's because we have that point of concurrency that's in the middle because we have the perpendicular bisectors that are equidistant. Okay, the next thing that we're going to be talking about is a special point of concurrency that is made up of our angle bisectors. All right, so just to remember, angle bisector is whenever you have an angle that is cut in half by a line or a ray. Okay, but an angle bisector of a triangle is a bisector of an angle of the triangle, okay? And the point of concurrency of the angle bisectors is called the incenter of the triangle. And it is always inside of the triangle, okay? So when we have the circumcenter, it could be inside, it could be on, or it could be outside, depending on what kind of triangle you had. But this time, whenever you have an incenter, which is made up of angle bisectors, doesn't matter the kind of triangle that you have, it's always going to be inside. So that's super important to us. Okay, so this triangle here, the special point of concurrency right here in the middle, point P, that is the incenter. And that is made up of angle bisectors. So if you take a look at all of the lines that we have here, the blue lines are those concurrent lines, right? They're made up of angle bisectors, and they meet up at point P, which is the incenter. Okay, we have a special theorem about an incenter as well. So let's take a look and see what that is as well. The angle bisectors of a triangle intersect at a point that is equidistant from the sides of the triangle. Okay, so again, let's see what that is. Equidistant means equal in distance. Okay, so we can say here's point P. That is the incenter, right? And we can tell we have an incenter by taking a look at these angle bisectors, right? So what we can say is that PD is equal to PE, which is also equal to PF. Okay, so I want you guys to write that down. PD is equal to PE, which is also equal to PF. Okay, so this time when you take a look, it's equal to the sides. Okay, so PE is equal to PD, which is also equal to PF. A little bit different this time. So now we're going to apply that to a problem. Okay, in the diagram, the angle bisectors of triangle JKL meet at point H. Okay, so that means that point H is our incenter. Okay, which segments are congruent? Well, here we have our vertices, right? Okay, we just learned a special theorem about this. So we actually know something that HN, HP, and HM have to be equal to one another because it says you have to be equal to the sides. So for part A, we're going to write that down. HM, so segment HM, segment HP, because we're talking about congruency, not equality, and HN are all congruent to one another. Okay, now for part B, it says we actually have to find the length, right? Because the actual segment sign is gone. Well, here's how you're going to do this. If you take a look at HN, and I'm going to highlight that for us in red, I actually see a triangle here, and it's a right triangle. So if we think about this, and I'm going to draw this triangle separately over here to the side. So this length is 24. We don't know this side, and we know that this length here is 25. Remember, we can use Pythagorean theorem anytime we have a right triangle. So remember, the hypotenuse is always across from the right angle. So we could do x squared plus 24 squared equals 25 squared, and that would get us the length of HN. So if we take care of that one right now, x squared plus 24 squared is 576 equals 625 for 25 squared. X squared, if you subtract 576 from both sides, would equal 49. And then again, if we square root both sides, your answer for x would be 9. I'm sorry, not 9. Oops, 7. Square root of 49 is 7. Okay, so that length has to be 7 for HN. Well, if we know that, then we actually know the lengths of HP and HM also, because we know that every single one of those lengths have to be equal to one another. Okay, so HN has to be 7. Well, then HP also has to be equal to 7, because we know by the theorem that we just learned, the concurrency of angle bisectors of a triangle, that because they are made up of angle bisectors, that point is equidistant from the sides of the triangle, that those lengths also have to be equal as well. So those ones would have to both be equal to 7. All right, and for our last problem for today's lesson, you can see that this last problem is made up of angle bisectors. So again, we're talking about an in-center, okay? An in-center means that we're talking about something made up of inside. We're talking about angle bisectors, so it means that these lengths have to be equal to one another. Okay, so now if we know that fact, we are asked to find the value of D in this problem. So if we know that XW is equal to WZ, we can now set up and say that 2D plus 7 is equal to 4D minus 1, because we know that those two lengths are equal to one another. So we're going to start solving for D. Remember, it's always better to move your variables first. Okay, so your value for D would be equal to 4. Okay, so just to kind of recap what we did today, we learned a lot of new vocabulary. Okay, so some important vocabulary. If we have a point of concurrency that is meeting up and made up of angle bisectors, it is called an in-center. And an in-center is always going to be lying inside of a triangle, no matter what kind of triangle you have. The other kind of special type of point of concurrency that we learned today, made up of perpendicular bisectors, is called a circumcenter. Okay, and a perpendicular bisector circumcenter, can be made up of triangles. If they are acute, they could be lying on the inside of a triangle. If it is made up of a right triangle, then it could be on the triangle. And if you have an obtuse triangle, it could be lying on the outside. And again, a point of concurrency is just where your three lines that you have that are made up on the triangle, wherever they meet up.